and welcome back. In this video, we will see some of the basics of pump performance curve. Before getting into the details of pump performance curve, we will see some of the basic terms or basic terminologies. Very much basic, will not go into the detail. First, let us understand why pump is specified in terms of head. Why not in pressure? Because we need the pressure of a working fluid, but in the pump specification or the pump manufacturer doesn't specify the pressure, or they specify in terms of head. Why do they do that? Let us understand that. We know that the pressure at any point of a working fluid at a certain height is given by rho g into head, where h is the height and g is the acceleration due to gravity and rho is the density of the working fluid. And we know that density of the water is 1000 kg per meter cube. And suppose if we take the density of the acetone, it is around 780 kg per meter cube. Since the height and the acceleration due to gravity is constant, the density varies with the working fluid. The manufacturer doesn't know what the consumer or what the industry or where it is installed, the what kind of working fluid is used. So hence the pressure in terms of Pascal or Newton per meter square, it is not specified. Okay. And next, now let us understand why we should choose the proper head. So it should be done carefully. A proper amount of head of a pump should be calculated. First, the total head is given by the head of the pump minus the head losses. We should calculate the total head and the head losses. Only then we can choose the proper sizing of a pump. Otherwise, it will be oversized or it will be undersized. We don't want those two cases to happen. So it should be done properly. See, the head losses can be due to two types, due to major losses and minor losses. Major losses and minor losses. And the minor losses may be due to sudden expansion and sudden contraction. And major losses, it can be found out using two equations, that is Darcy-Weisbach equation as well as Chassis equation. All those things, from those things, you have to calculate the head of the pump properly. Okay, and now we'll see the term called NPSH. What is this NPSH? Net positive suction head. Okay. It is the minimum pressure at the suction of the pump, suction or inlet of the pump to prevent cavitation. Now you might be wondering what is the term cavitation. It is a phenomena of rapidly It is the phenomenon of rapidly expanding and collapsing bubbles, which tend to destroy the surface of the impeller as well as the casing. It eats away the surface of the material. This happens because at the low pressure is created at the inlet of the pump. At low pressure, even at the low temperature or the low atmospheric temperature, the working fluid begins to boil, and these rapidly expanding and collapsing bubbles hit the surface of the impeller as well as the casing. It destroys the surface, and hence it will lead to lower life. That is why NPSH is very much important. We should always try to prevent cavitation. Okay, now the basic terms we have understood. Now let us go and understand, let us draw some of the pump characteristics curve. Okay, on the x-axis and on the y-axis. On the x-axis, we have the flow rate, that is Q. It may be in terms of meter cube per second or liters per second, or it may be in terms of gallons per second. And on the y-axis, we have the head. It may be in terms of meter or in terms of feet. Okay. Now, when we plot the graph of the head versus the discharge, we get something known as like this. Here we'll mark the two important points, that is A and this one as B. Okay. At A, this is for a given pump, okay, only a pump. At point A and B are very two important points. At point A, what happens is head will be maximum, but Q will be zero. There will be no discharge. Discharge will not be there. And at point B, Q will be maximum, that is the flow rate will be maximum, and the head will be zero. Okay, these two are very two important points when we plot the pump curve. Okay, and now let us do another graph on this. The efficiency. Initially, for a pump, the efficiency increases slowly, and then after reaching a certain point, it gradually drops. There's some point where you will get the maximum amount of efficiency. Always the pump should be maintained 10% of this point, plus or minus 10%, plus or minus 10% of the maximum efficiency in order to minimize the wear and to increase the life. Always the pump should be maintained within that range. Okay, and the next point is we'll be drawing the power consumption. As the discharge increases or the flow rate increases, the gradually power consumption also increases. And this is the power, and this is the efficiency, and this is the head versus discharge. And what happens to the net positive suction head when the flow rate increases? That one also increases. We can see something graph similar to this. This is NPSH, net positive suction head. Net positive suction head also increases when the flow rate increases. Okay, and now let us go and see the other performance characteristics. This is the basic general pump performance curve characteristics or the graph. Okay, now let us do a combined graph, that is family of curve. Whenever we buy a pump, they will give a family of curves chart. Now let us understand what is exactly is the family curve of the pump. Okay, now again I'm going to draw a graph. Okay, and now let us plot the very important parameters. This is also the same on x and y. We'll be having the same. On x, we'll be having q, that is meters per second, or it may be in liters per second, or it may be in gallons per second. And on the y-axis, we'll be having the head. It may be in terms of feet or in terms of meter. Okay. And now let us draw. See, this will be the head versus the discharge curve. And we'll draw one more head versus discharge curve. We'll understand it. This performance curve, we are plotting it for a constant speed, constant impeller speed. Okay, always remember this. And now let me draw the diameter, and this performance curve is obtained. We are getting different curves, right? Different HQ curves. That the reason due to that is this is the diameter of the impeller T1 for different diameter D2, for different diameter D3, and for different diameter D4. Always in this, D1 is always greater than D2, which is always greater than D3, which is always greater than D4. Okay. And now let us draw another curve that in that we will be indicating the efficiency. Before going into the efficiency, we will be marking the power curves. Okay. This dotted line or the dashed line is the power curve. It will be measured in terms of HP or kilowatts, whatever may be the unit. This is the power. Okay, and let us name this one as P1, P2, and P3, P4. And this P1 is always greater than P2, which is always greater than P3, which is greater than P4. This one is also very important. And now we'll be marking the efficiency. This one is efficiency. Say this one is neta 1, and this one is also this point, and this point will be neta 1, and this point will also be neta 1. Okay, here we'll be getting the maximum efficiency. And say this one will also be neta 2, neta 2. This one is neta 3, and this one will also be neta 3. This one is neta 4. These corresponding points, these are the values. N3 corresponds to these two values, N2 corresponds to these two values, N1 corresponds to these two values, and N4 corresponds to these two values. Okay, these are the important points. Okay, and always in this, neta 1 will be greater than neta 2, and then neta 3 will be greater than neta 4. This is the diameter of the impeller, diameter of the impeller. This one is the power, this one is the efficiency. Okay, we can notice that over here as the diameter decreases, the power consumption also decreases, but the efficiency drops. Okay, we can see that N4 efficiency is lower than N1. As we increase the diameter, we will get the maximum amount of any efficiency, but also the power consumption will also be very high. Now let us look into a real family of curve of a pump. In this graph, we can see that the pump is given at a constant speed of 1750 rpm. And on the, as I told, the head is measured in terms of feet. Okay. And here in this Q is measured, sorry, it is measured in terms of gallons per minute. And the net, this is actually the NPSH curve, that is net positive suction head. In terms of feet, it is given, that is the head. And here, when we look into it, this is the dark line is the discharge versus head versus the discharge. Okay. And here you can see this kind of curves. That is the efficiency. Here you can see that at this point to this point, the efficiency is the same. That is around 79.5%. And when we go to this point, that is over here and here, the efficiency we get is 79. As we go further, the efficiency decreases. See here at the ends, we have extreme ends, we have low efficiency. And here you can see these numbers. What exactly are these numbers? These are the diameter of the impeller. As I told before, the diameter of the impeller decreases, the efficiency also decreases, as well as the power consumption also decreases. Here you can see this line. This is the power consumption. See, this is 5 HP, this is 7.5 HP, this is 10 HP, and this one is 15 HP. So, as the diameter decreases, the efficiency also decreases, and the net positive suction head also decreases, and the power consumption also reduces. Now, let us this is how actually the pump curve is read, and this is the combined curve, and this combined curve is known as the family curve of a pump. And along with this, you need to learn some calculations, which are very much essential. So in this, we'll see some. How do you find the head? Suppose if you need a discharge of say 500 gallons per minute. Okay, if you need a discharge of 500 gallons per minute, and you need to find the head and its efficiency. See, I'll be getting the head to be somewhere around 65, 64, something like that. That is 64 feet, and I'll be choosing the diameter such that it will be 8 inches, the impeller diameter, and the power consumption as it just crosses over here, I'll be using the 10 HP. Okay, in actual case, what we'll be doing is we'll go for a slightly higher power, and that way we can compensate any miscalculations in the head. Okay, but there you'll be getting a higher diameter, but the diameter can be trimmed. The diameter of the impeller can be machined to make it small so that we can get the appropriate amount of power. We can also reduce the amount of power by using the pump affinity laws. Some laws are there. If you know any two values, you can find out the other one. Using those calculations, you can go for a slightly higher value and then decide which one to use. Always, as I told in the graph, suppose in this graph, say uh, let us wait. Yeah, I'll go for this one. Yeah. Suppose I want a head of, I want a discharge of say 1000 meter cube per second. Okay, I will draw a straight line from this point. Okay, so I'll be getting this, and suppose I'll get from this point, I will draw a straight line, straight horizontal line. I'll get some heads, suppose say it is around 100 feet. This is the typical values, not the exact values. This I'm giving the example. For this, I'll be getting some diameter D3, which is efficient, which is more than enough. Okay. but I'll be selecting the pump of a higher power. If I select a pump of higher power, then I'll be giving a maximum diameter. So, what the manufacturer does is, or what the user does is, according to his requirement, he will trim down the impeller size. That trimmed impeller size can be machined, and it can be made to suit our requirements, and we can also modify the discharge as well as the head from it. Those calculations are there, which we'll be finding out using the pump affinity laws. Those laws and some calculation basic will be dealing in the next video. And thank you for watching my video. Please do like and subscribe my channel for more videos like this, and comment below for any suggestions.